If you return back to the table, to the binomial table, as we discussed, as I said previously, it's a cumulative frequency. The probability of it, the table, give us a probability less than 0.5. Now, how can we solve the problems that have probabilities of more than 0.5? Since the table doesn't have probabilities, doesn't give us the probabilities of more than 0.5. For this, we do need to solve it like this. First of all, we do need to restate the problem. Now, if you have a problem that has probabilities, or the probability of the success is greater than 0.5, we do need to restate now we do need to restate the problem in terms of failure, in terms of 1 minus p, rather than in terms of success p, because as we discussed, as we explained previously, that the probabilities that have been inserted in the table is not more than 0.5. So if the probability is more than 0.5, the first thing to be done is to restate the problem in terms of failure. Now, if we have, for example, the probability of 0.8, for example, and 0.8 is not found in the table, we do need to restate it as a failure. So 1 minus 0.8 will yield 0.2, and 0.2 can be found where? In the table. This is the meaning of the first thing. The second is we do need also to think for the number of failure, which is n minus x, rather than the number of success. Previously we were thinking about the number of success, which is x. Now we do need to subtract the total number of selected samples minus x, rather than x, because x here, since we think about the in terms of failure, not success, not success, we do need to take the n minus x rather than taking x also. This is how to solve the problem which are more than, the probability of them is more than 0.5. The statement will be as follow, as you see here. Now, the probability of x, large X, equal to x over n, comma, when the probability more than 0.5, greater than 0.5, will equal to the probability of large X equal to n minus x. This is the number of failure, n minus x, given that n, comma, 1 minus p. 1 minus p is the failure probability. This is the probability of the failure, as you see here. N is the, as you see, the sample size, n, and also we will treat the probability of failure as thought is where the probability of the success. Directly, just only treat it as failure. The failure, we treat it as the success. Now we may obtain the cumulative frequency from the table using the following relationship. When p is greater than 0.5, the probability of large X is less than x given n, comma, when the probability is greater than 0.5, equal to the p equal to large X greater than or equal to n minus x, given that the number of n, and the failure probability, which is 1 minus p. When x is greater than or equal to some x, when p is greater than 0.5, we use the following relationship. This is the main relationship that to be used for solving such problems that have probability of greater than 0.5. And again, why do we need this thing? Because the distribution, binomial distribution table, does not give us probabilities more than 0.5. This is why do we need to use those equations. This is the main equation to be used for solving such equations. Now we will take an example. in a certain community, on a given evening, someone is at home in 85% of households. A health research team conducting a telephone survey selects a random sample of 12 households, use the binomial table to find the probabilities. Now, we do need to understand this equation before commencing in its solving. Now, in a certain community, the probability of someone is at home is 85%. From this value, from this probability, we do need to understand that this is a probability which is greater than 0.5. Now, we do need to restate the problem. We do need to think about the table. This table gives us not more than up to 0.5 probability, and this probability is greater than 0.5, which is 85%. Now we do need to restate our problem to think about the failure, not the success. And we have 12. What if a team conducting a telephone survey in a random sample of 12 random sample of 12 households, they call 12 houses. What is the probability that the team will find at home in exactly 7 households? Exactly again. Now, we restate the problem as, since we are thinking about the failure, not the success, what's the probability that the team conducting a survey gets no answer from exactly 5 calls out of 12 if no one at home in 15% of the households? Why do we restate this problem in this way? Again, because the probability is much more than 0.5. The table doesn't cover this probability, and we do need to solve it by using the table, distribution table, binomial table, I'm sorry. So now if you look to those numbers, it's totally different from the previous of the origin example. Now we are dealing with 5, not 7. The question was exactly 7 households. Why can we convert it into 5? Because 12 events, 12 calls, and we do need 5. 7 is the success. Now we do need to think about the failure. The failure number, 12 minus 7 will equal to 5. This is the failure, and we will treat it as success. If no one at home in 15%, sorry. Now, from where we get 15? The original probability is 0.85%. Now, 1 minus 0.85 will yield 15%. 15%. This is how we restate this problem again. Now, we are dealing with this probability. What's the probability of large X equal to 5 over n equal to 12? N here is equal to 12 because n equal to 12. The probability is more than 0.15. Now, the probability of X is less than 0.5 or equal to 5 minus the probability of X less than or equal to 4. Because we are asking about exactly 7. Exactly 7%. 7 households, sorry. So, it's exclusively, حصريا. So, we take 5 minus point. The probability of X is less than or equal to 4 from the table by using 15% probability. From the table again, it is this number from this number, it will yield 0.0193. From where we get those numbers? From the binomial table directly. The probability of X less than or equal to 5 is 0.9954, and given that the P equal to 15 and X equal to 5 from the table directly. Okay? And also the same for the probability of X less than or equal to 4. Now, the second question was the probability the team will find someone at home in 5 or fewer households. 5 or fewer. 5 or fewer at home. The probability we want is that one. Sorry. Oops. Now in this case, the probability of x is less than 5 when n equal to 12 and p equal greater than 0.85 will be the probability of x greater than 12 minus 5. Why 12? Because the total number of selected samples, randomly selected samples, minus 5, and we stated previously that we need to take the n minus x, when n equal to 12 and the probability is equal to 0.15. 0.15 because 1 minus 0.85 will yield 0.15. From the table, it is a complementary, as you see, the probability of x less or greater than or equal to 7 when n equal to 12 and p equal to 0.15. It's a complementary probability that obligates us to take 1 minus this probability of being less than or equal to 6 when n equal to 15 and p equal to 15. N equal to 12 and the probability of 15, and from the table it is 1 minus 0.9993. 0.9993 we take it from the table when the probability is 0.15 and n equal to 12, taking that x is less than or equal to 6. This is the final answer. Third, the team will find someone at home in 8 or more households. 8 or more. 8 or more. Directly, it will be 12 minus 8, it will yield 4, and also the probability 15, and this is direct one that equal to 0.976. Now you do need to spend much more time going back to this textbook, solving some problems, train yourself how to use the distribution table, the binomial distribution table. It's very important to understand the values, how can we get them, and how can we use them in solving such problems. Now we go to the expected values and the standard deviation from the binomial random variable. For a binomial random variable x based on n trials and success probability of p, we can obtain the mean by using mu equal to the expectation of x equal to n times p, and the standard deviation will be sigma equal to the square root of the n times p multiplied by 1 minus p. As an example, this example is using the extraterrestrial life, extraterrestrial life. 50% of large population would say yes if asked, do you believe there's an extraterrestrial life? 15% from this population will say yes. Do they believe? Yes, they do believe. 50% they believe in this thing. Sample of n of equal to 100 is taken. We took 100, n equal to 100, and the probability is p equal to 15. X, the number of samples who say yes, is approximate binomial random variable. The mean will go directly is np. Okay, n is 100 multiplied by 0.5, which is the probability, equal to 50. This is the mean, and the sigma or standard deviation will equal the square root of 100 multiplied by p and q. Okay, 0.5 multiplied by 0.5, square root will be 5. In repeated samples of n, this is the final conclusion from this question, and repeated samples of n equal to 100, on average 50 people would say yes. The amount by which that number would differ from sample to sample is about 5. This is the amount, the differences between the samples.